right, hello everyone. I'm Joelle Sarlls. I'm a staff scientist in the NIH MRI research facility down in NMR Center, so like a sister facility to MRI. And today we're going to do something a little bit different. We're going to talk about diffusion MRI. So I'm delighted to be here to talk about one of my favorite topics. This is, an educational course, so I'm going through the very basics, and so please feel free to ask questions at any time. I'll see if I can monitor questions on Zoom, but Pete, if you can help me with that, that'd be great. Okay. So why cover diffusion imaging in an fMRI course? Well, for those doing fMRI studies, I think they may be interested in diffusion imaging as it can provide information about the underlying white matter of that activated cortex. So as you already know, magnetic resonance imaging provides information about the spatial distribution of water. So in diffusion MRI, we get information about the motion of the water. And DWIs are sensitive to cellular architecture and the tissue integrity. And DWI can provide quantitative measures that can be directly compared between participants and over time. And diffusion imaging can be used to identify specific white matter tracks to go along with your study. So DWI is a good tool to use for studying anything that may change the structure of that tissue. It's a very sensitive technique, but it's not very specific. So here's an outline of my talk. I'm going to first explain what is diffusion, how do we measure it with MRI, how do we extract directional information from the diffusion, what are some of the practical problems and limitations with using diffusion-weighted MRI, and then I'll touch a little bit beyond the diffusion tensor. So first, what is diffusion? So diffusion refers to the random translational or Brownian motion of molecules that results from the thermal energy of these molecules. So here's my little molecule. We're talking about the protons on water, so those are the molecules that we're going to be talking about for imaging. So under thermal energy, it's going to have this random movement, and then the diffusion coefficient is directly proportional to the temperature, and then inversely proportional to the viscosity of the solution that molecule's in, and then also the size. So if we have a large number of particles that are free to diffuse, then this has a squared displacement of the Gaussian form. So in one dimension, what that means is if we have a large amount of particles that we start at a zero position, and we allow them to diffuse for some time, then it will give us this, this Gaussian form, this like bell shape. And it is related, let me see what happened to my mouse. There you go. To the diffusion coefficient, and then the amount of time that we allow. So the more time that we have, the bigger that will be. If the diffusion coefficient is higher, the bigger that will be. When we look at that in 2 dimensions, then what we have is this cone shape here, and in 3 dimensions, that would be represented as a sphere. Okay, so we can calculate how far a water molecule will diffuse in a typical 3D voxel for our MRI experiment. So if we think about a voxel as like 2 by 2 by 2 millimeters, then we have roughly 10 to the 20 water molecules, so that's a very large number. And at body temperature, at 37 degrees, the diffusion coefficient, the free diffusion coefficient of water would be about 3 times 10 to the minus 3 millimeters squared per second. So if we allow this ensemble of water molecules to diffuse for about 30 milliseconds, then they will have gone about 25 microns. So that's a good distance for, for in vivo tissue. So if the motion of water is hindered by cell membranes or macromolecules, then this is how we can get contrast in that image. The displacement will be less than that free diffusion coefficient, and it'll appear as a lower signal. Okay, so how do we measure diffusion in MRI? So we have a variety of physical properties of tissue that we look at in MRI. So we have proton density, the T1 relaxation, T2 relaxation, T2 star in our normal types of images. And we can control how much contrast we have. What does the image look like? Does it look like T1 or does it look like T2? Based on the type of sequence that we use, what is the TR that we use in our experiment, what is the echo time, for example. So now on top of that image intensity that we already have, that contrast we already have in our MRI, we're going to add this physical property that is the diffusion coefficient, and we are going to use the B value to weight our image to that physical property. Okay, so before describing the V value, I want to take you back and let's recall that the resonance frequency of our protons is directly proportional to the magnetic field that it experiences. So our main equation for MRI, which you can leave the functional MRI summer course knowing, which I'm sure you did, learned in your basics already, is that omega equals gamma B. Gamma is that gyromagnetic ratio for hydrogen protons, and B is that magnetic field. So that, if we're just sitting at 7 Tesla or 3 Tesla, then everybody should be resonating at the same frequency. When we turn a gradient on, what it does is it adds a little bit of more magnetic field in one direction. So here I have a gradient in Z, so it adds more magnetic field in this direction and less in that direction. So now the protons that are over here feel a higher magnetic field, and they're going to rotate a little faster, and the ones that are over here feel less magnetic field, and they're going to process and rotate a little slower. So now we've got this equation for our frequency. So that's what we're going to use to do our diffusion weighting, to say something about where these molecules are and how they're moving. So after, this is a little diagram of a pulse sequence. So after our 90-degree excitation pulse, all of the protons will be tipped into the transverse plane, and they'll all have the same phase. They'll all be lined up, no matter where they are in space, no matter where they are in X. That gives us this net magnetization. So what we're going to do now is turn on a gradient for some amount of time, and depending on where they are in this position, they're going to process a little faster or a little slower. So here's my cartoon. Now we've got a dispersion of that phase based on their position. I like to think of this as a phase twist in space. So some went faster, some went slower. So now we've got this phase twist set up. Now we're going to turn off the gradient and let some time go and allow these molecules to diffuse, this random motion to occur. So now we've had some time here. This is our diffusion time. And now if I'm going to put on an equal and opposite gradient, then if something has not moved, they will exactly line back up, and I will regain that net magnetization. But in this biological environment, what's going to happen is some of them will have moved, and so we will not regain, they will not all line back up, and the effect of that is that the net magnetization is now lowered. Sorry, I'm having trouble with these multiple screens and my pointer. Okay, here it is. Net magnetization is a little lower, so that's the effect of the diffusion. And that will, how much lower it is will depend on how many of those molecules moved, how far did they go, and all that. So, okay, so now let's get a visual of this in real life. So we're going to play a little game of guess the intensity. So here I've got two containers. The small one has a viscous polymer and water solution in it, and the large ball has distilled water. These are both at room temperature. So this is what the image looks like with no diffusion weighting. They're about the same signal intensity, right? So now we're going to do this diffusion weighting. Which one of these do you think the molecules will move more? The viscous polymer or the free water? The free water, exactly. So what's going to happen to the signal? Will it be less in that big one or more in the big one? So it is less because the water moved more, so now the signal dropped more because of that diffusion. Okay, so now you've got a concept of it, visual concept. Okay, but when we're doing actual MRI in human tissue, we're going to actually use a spin echo diffusion prep, and so this is so that we can avoid the effects of the static field inhomogeneity. So we're going to actually use a 90 and a 180, which will refocus those static field effects, and we can just have our diffusion. So now our diffusion prep looks like this. So here's our one that does the phase twist and the one that does the untwisting. How much diffusion weighting we have in the image is going to be directly proportional to this, the amplitude of our diffusion gradient and how long we turned it on. So this is like the area under that gradient curve, and how long we let the diffusion occur. So this is our diffusion time. And these go into our equation for the B value, which is that parameter we get to control, because we can make our gradients any size we want. So the B value now is directly proportional to the square of the area of that diffusion gradient and linearly proportional to the diffusion time, big delta. Okay, and now we can put this all together. So the signal we'll get when we turn the diffusion gradients on is equal to the signal we would have had with no diffusion weighting, multiplied by e to the minus bd. So this is, again, the parameter we're controlling, the b value, and d is the diffusion coefficient, which we want to know. So to give you a better feel for this, for DWI, I listed some of the typical scan parameters we would use on our 3T clinical scanners downstairs. So we do a single shot spin echo, echoplanar imaging. So EPI is the same type of acquisition that's used for typical fMRI. That single shot EPI, and the spin echo part is that 9180 I showed at the beginning. So just to give you an idea, the TEs we're talking about in diffusion is 50 to 100 milliseconds, depending on how good your gradients are and how much p-value we want. Our TRs are 5 to 10 seconds. We want to have a fully relaxed signal. We want our T1 of our white matter and gray matter, we want that to have fully relaxed because we're already killing the signal with our diffusion weighting, so we want as much as we can have to do that, to have higher SNR. A typical matrix size would be 120, so we have like a 2 by 2 millimeter in plane, a 2 millimeter slice thickness, and we try to keep isotropic voxels because we don't want the coherence of the tissue in any one dimension to bias the results. So we want that size of the voxel to be consistent in the dimensions. And B values for brain are around 1,000 given what the diffusion coefficient of brain tissue is. So, okay, so here's another ball of water, and I'm just going to show you what it looks like as we start to increase the diffusion weighting. So this is just, it's hard to get natural zero. So this is a B value of 8, and then you add a little more B value, a little more, a little more. If you take the intensity from one voxel and now plot that, you get a nice exponential curve like this. So we've got our different B values and the different signal intensities. So given our equation, we know what S naught is over here. We've got the B value and what the S is. With those, we can calculate on a voxel by voxel basis what is the diffusion coefficient. And typically, this is done by taking the log of the equation and fitting the linear form. Okay, so that's all the phantoms for now. Now let's look at some brains, which is what we all, I'm sure, love to look at. So now we can do the same thing in a brain image. So now you've got the B0 image, the non-diffusion coefficient or non-diffusion weighted image. And it looks like a T2 contrast because of that TE and TR. And it's, again, collected with EPI. And then if we add diffusion weighting, here we have put it on in the Z axis, so that's like in and out of the plane. You can see there's a reduction in signal, like the CSF, which is pretty much free water, is gone. And then there is some varying contrast within the white matter. And you can do the same thing and calculate what is the diffusion coefficient in Z for this slice and get that image. So you can see here that the diffusion coefficient in Z is not consistent across the brain. And so why is that? It's because the water is not free in tissue. So in brain tissue. So here is an EM, electron micrograph of a mouse corpus callosum. So we're cutting through the cross section of the corpus callosum. And you can see that there are barriers for the water molecules to run into. So the water is not free. There is cell membranes, and then this black here is the myelin sheath around the axons. There's organelles within the cells. There's the extracellular matrix between them. So there's a lot of stuff that the water runs into. And you can imagine that if you're a water molecule within this axon, you're going to run into some barriers this way, and then along the length of it, you'll be able to move a little more, where if you're water in between the cells, you're going to be running into different barriers. And so the water diffusion is not the same in both directions, and it's anisotropic. So for this example, when we've got our water molecule that's within the axon, the diffusion perpendicular to that length of the axon, so the perpendicular direction of diffusion will be one thing, and then down the length of it will be another. You'll be able to move much farther down the length of it. So the diffusion perpendicular is much, much less than parallel, so it's an anisotropic diffusion. So if we want to know what the average diffusion is, then we need to get rid of this directional dependence. And so if you want to do that, the minimum amount of data you need to collect is your B0 image, so non-diffusion weighting, and then we need diffusion weighting in at least in 3 orthogonal directions. So I've got these images here. We have X, Y, and Z. You can see in X, for example, that the corpus callosum has got a low signal because it can easily move down the length of that axon, where if we look at Y, or in particular Z, in and out of the plane, that it's bright because the water ran into that myelin in that cross-section and couldn't go very far, so it's not as dark. So we can take the geometric mean of these 3 images and then do the same calculation, and now we can calculate the apparent diffusion coefficient, so that's like the mean diffusion coefficient for every voxel. And it's interesting that the contrast, the mean diffusion coefficient across the brain is pretty flat, it's pretty consistent. So that's nice, it's nice homogeneous. And this is what was used initially in diffusion imaging to look at different types of pathology. The main one was acute stroke. So here we can see in our normal diffusion weighted image, there's a variety of hyperintensities. But when you do that diffusion weighting piece and you get the that average diffusion image, you can see the area of stroke just pop right out. And you can calculate what is the actual diffusion coefficient there. So this is, a quantitative map. And we can look and say on the contralateral side where you've got healthy tissue, your diffusion coefficient is about what we expect, about 0.7 times 10 to the minus 3 millimeters squared per second. And then in that area of stroke, it's dropped by almost half. So this has been used for a long time clinically. Now what if we want to say something about that directional information? Well, how can we extract that? Well, instead of looking at the average, like I said, we want to look at this directional information. So recall that our white matter has many structures that it's going to run into. And I wanted to bring this back up to say that our typical imaging voxel, being like 2 millimeters, is 200 to 300 times bigger than what I'm showing you here. So we have lots of axons and cell bodies and other stuff within our voxel. So here I'm going to just say, a whole group of these axons, if they're nicely coherent, would look something like this. And if we let our water diffuse along those axons, then that propagation would look something like this. And that we can, if this is, if it's Gaussian diffusion, but it's not consistent in all the different directions, then this can be represented as an ellipsoid. And that's Gaussian, that represents Gaussian, characterizes Gaussian diffusion where that's not equal in all directions. So we can do it with an ellipsoid. And this ellipsoid can be described by the diffusion tensor. So the diffusion tensor is our mathematical representation. It's a 3x3 matrix that was described by Vassar et al. Back in '94. And the tensor has been shown to be symmetric. So that means that for this ellipsoid, we need measurements in at least 6 diffusion directions to be collected to be able to calculate our 6 unknowns. And then the whole diffusion tensor can be filled in because it's symmetric. Okay, so that means to do DTI, the absolute minimum amount of data we need is our V0, and then diffusion weighting in 6 different directions, 6 different non-collinear directions. And now we can calculate that diffusion tensor on a voxel by voxel basis. And here's an image of the calculated diffusion tensor components. So note that the ones along the diagonal are actually the diffusivities in the 3 orthogonal axes. So this is diffusion in the x direction, in the y, and the z. But the off-diagonal elements actually correspond to a correlation between the displacements between these orthogonal axes. So the diffusion tensor, we can take it, we can do some math to it, we can diagonalize it and get and change the frame of reference to be that of the ellipsoid and get the major and minor axes of the ellipsoid. And with that, we get our eigenvectors and eigenvalues. So the eigenvalues are here, so the highest one, the primary eigenvalue, and down from there as far as its size. And then here are the eigenvectors that correspond with those eigenvalues. And once we have this, then we can do some things that you're probably familiar with if you've looked at any diffusion literature. So we can take this and calculate our average diffusivity. Sometimes they call this the trace of the diffusion tensor. So this is just the average of those eigenvalues. We can also say how different are these eigenvalues. Tell us something about the shape of this ellipsoid, and that's the fractional anisotropy. Fractional anisotropy goes from a value of 0 to 1, so it's this line right here. It's a nice linear relationship. If it's 0, it's a sphere. If it's 1, then it's like a pencil. So, going on there. All right, so what does this look like in the brain? So here's the mean diffusion coefficient. It looks like the ABC map. And then fractional anisotropy here, it shows a difference in the white matter and the gray matter. In addition, even the white matter has some heterogeneity within it, and this is because the direction of the white matter is not consistent within some of those voxels. So you can see, like, here it's very anisotropic because they're all kind of nice and coherent, but in this area we're going to have more than one type of, more than one direction of that white matter going in different directions. So now the anisotropy is low because it's all partial volume, it's all combined in that one voxel. Okay, so the direction of the anisotropy can be color-coded. This might be what you've seen the most. So we can take our ellipsoid here. We've got our main eigenvector. We're going to assign different colors to the directions. So X is typically red, Y is green, Z in and out of the plane is blue. And for this voxel, if this is the ellipsoid, then that primary eigenvector is pointed along X, so we'll call it red. We can do this for every voxel in the brain and get our directionally encoded color map. So you can see the corpus callosum here is red, and then we got these motor fibers that are running, from the top down towards the spinal cord. And the color wheel here shows all of that. So red, right, left, green, up, down, and blue in and out of the page. But we can do other things with that. So that's what you typically see. So that's the directionally encoded color map. But in this color map, that's the typical representation. Positive X and negative X, positive Y and negative Y are like the same color. Positive, negative X are the same color. But it doesn't have to be. So if you want to see something about that, how it's coming together, you can do a no symmetry type of color map. This is kind of hard to see probably from your distance, but this is a line field. This was like pre-tractography. So you take that ellipsoid and you make a line for that primary eigenvector and put it in every voxel, and tractography is basically connecting all these lines. But we can also say something about the shape of the ellipsoid, which some people have used. So we have linear, planar, and spherical. So linear would be that it's prolate, kind of like the shape of a football. Planar would be that it's oblate, like an M&M, and spherical, obviously, a sphere. So there's other ways to represent this data. And DTI has been applied to many different clinical applications. So stroke, for example, cancer, and then the effects of radiotherapy on the cancer to see if it's, if it's affecting the cancer as a treatment. Let's say epilepsy, normal brain maturation and aging, dementia, and then more recently people have been using it for connectivity, which you may have heard, and that is using tractography, which we will discuss a little bit more. But I wanted to show you one of the clinical examples that I worked with, which is pediatric diffuse intrinsic pontine glioma. So this is just a regular T2-weighted image through the pons of this patient, and you can probably see that the pons is a bit enlarged here. And now if we look at the mean diffusion coefficient and the fractional anisotropy and the directionally encoded color map, and I put a healthy pons here in case you're not used to looking at this region of the brain with diffusion imaging. But you can see in the patient that there is a high mean diffusivity here in the pons. That could be edema or maybe necrosis from the tumor. You can see that the anisotropy is low in some of these white matter tracts, which could indicate infiltration of other kinds of cells or maybe a breakdown of the axons there. And then in this directionally encoded color map, you can see that these transverse fibers, maybe they're intact, but they've been pushed and changed in location. Here's just one example. Okay, so a couple more little quizzes here just for fun. Make sure you're awake before we go on to the next set. So, okay, so this is histology image and the dark rings are again myelin. So we've got a cross section of white matter, corpus callosum. So what do you think? Ellipsoid is like sphere or prolate like a football for our corpus callosum? Prolate. Yes, prolate, that's right. It's this one. Woo. Okay, and then the gray matter, which is much more heterogeneous, not as much, you think, more spherical or more prolate? Yay! You guys have done very well. Okay, so now we're going to take a little sidestep and talk about the practical problems and limitations of doing diffusion imaging. So now you're all excited, you want to go do some diffusion imaging, and it's easy to sit down at the scanner and collect diffusion data, but like fMRI, it's no easy task to successfully carry out a good diffusion experiment. diffusion study, I should say. So let's talk a little bit about that. So typical diffusion-weighted imaging is collected with single-shot EPI like fMRI. One of the pros is that it's time efficient, so you can get the whole brain, all 60, 80 slices collected in about 5 seconds, which is good because we are looking at the motion of water, so any kind of bulk motion will be a problem. So if we collect fast, we can try to avoid that bulk motion. In addition, we have to collect lots of volumes of data to do our calculations, so we don't want to have our subjects in there for too long. But some of the cons that are similar to fMRI is that it's inherently low in spatial resolution because you do have to collect all that data in one excitation. You also have distortions of the shape of the brain and of your image due to field inhomogeneities. And then for diffusion imaging, we have another type of distortion that's due to that diffusion preparation period from eddy currents coming off of those big gradients that we use. So the first con, this field inhomogeneity. So this is a T2 weighted fast spin echo image. So this is pretty much as close to the true shape of the brain as you can get. If we look at our single shot EPI image without diffusion weighting, I've put the outline here on it. You can see that it's compressed a little bit, so that's that distortions due to just the EPI acquisition and the field inhomogeneities. And you can see there's some signal pileup and dropout, which is typical. We can try to, in post-processing, correct for that global shape change by warping the single-shot EPI image to an anatomical image. So we can help with that. But it's hard to get rid of the signal pileup and dropout unless you collect multiple phasing codes. But we can do that too. But for diffusion weighting, what I'm going to do here is go through a movie that's going to show you different directions. And you'll see that the brain kind of jiggles a little bit when you go through the different directions for the diffusion, and that's the distortion that's due to the diffusion preparation period. But we can correct for that too in post-processing. Here's after correction. You can see it's nice and lined up, and then you might ask yourself, well, post-processing is a pain because the code's always changing, and I have to rerun things. So do I really need it? The answer, of course, is yes. So here's our FA maps if you don't do anything, and if you do, you can see that the areas of low anisotropy are too high if you don't correct for that, and that the areas of high anisotropy will be calculated lower, so it kind of compresses your values. And if you do some post-processing, you can get a nice, clean FA map. There are some other common problems that I see in DTI all the time that I want people to be aware of. One is low SNR. In general, like I said, the acquisition is already inherently low, and then we're adding diffusion weighting, which is low, so we're always working with low SNR. Incomplete fat suppression is another one that I see even in published images quite a bit, and then bulk movement and cardiac pulsation. And I'll say these two you need to be aware of at the beginning because you cannot correct for those in post-processing. There's some things we can do about bulk movement and pulsation, but you cannot do anything. If you have a low SNR image, that's what you're stuck with. So here's, to give you an idea of that, how do I know if the SNR is too low? So here's our B0 image, so before we do diffusion weighting. I got a 2.5 millimeter isotropic voxel, so 2.5 in all dimensions, 1.7 down to 1.3, and you look at this one and you think, oh, the signal's still pretty good, right? But then you add your diffusion weighting, and this is what it looks like. So now this piece of white matter at this resolution, you can still see that that the signal's gone down, but it looks higher than that background noise. You get to this resolution, and you can't tell the difference between that and the background noise. So now all you're going to be calculating is the noise when you try to get your parameters. And people, when you're sitting at the scanner, you think, oh, I'm going to go from 2.5 to 1.7, like I changed it some. No, but if you think about your voxel volume, you've gone from 15.6 millimeters cubed to less than 5. So you're, down to a third of what you started with. So it changes quickly using isotropic voxels. And yes, this does affect your calculated parameter map. So here's the FA with those same changes in resolution, and you can see that noise, again, compresses that your range of fractional anisotropy values that you can get. Incomplete fat suppression, so here it is. Fat resonates at a slightly different frequency, so the protons in fat resonate at a slightly different frequency than the protons of water. We can see them with our imaging. Diffusion coefficient of fat's very low. So if you look at the non-diffusion weighted image, which I didn't put here, it's hard to see the fat in that one. But when you add the diffusion weighting, now you can see it. So because it's at a slightly different frequency, it's a shifted image compared to the water, and it's right here. And because that diffusion coefficient is different, you see it in the mean diffusion, and then also in the fractional anisotropy maps. You don't have to live with this. This is usually the scanner. Maybe you just redo the pre-scan. Often it's the shim's not so good, or it didn't find quite right, the center frequency quite right. So if you stop, redo the pre-scan and collect again, it'll typically go away. But people don't often look at their data when they're acquiring it. So it's very important to look at your data because there's not much you can do with this afterwards. Cardiac pulsation, I throw this in there as an example. So we are looking at the motion of water, so even these bulk motions you'll pick up. So if I have diffusion weighting in Z, what happens in cardiac pulsation is that there's blood that comes into the brain, and the skull is a fixed volume. So the spinal cord and the midbrain actually bob up and down, kind of come out of that skull a little bit. So if you're weighting in that direction, then you actually see that, and you get a big signal dropout right there in that midbrain section. But you cannot actually take care of this with robust tensor fitting algorithms that will look for that kind of dropout, but it's something to be aware of. And then one more is the bulk movement. So this is also part of that processing. So the EPI, single shot EPI, is insensitive to bulk movement, but if the movement is big enough, and especially if it happens during the diffusion preparation period, then what will happen is it'll be a shift of your K-space data, and if the shift is big enough that the energy goes outside your acquisition window, then your image becomes just noise. And that's what you see here. So this is an axial slice that is starting to go into being just noise. I took a stack of these axial slices and I'm showing them to you in the sagittal plane, and you can see all these slices that were affected by motion that are now just noise. So if you're going through your data before processing, and you need to see are there volumes with different diffusion directions where someone was moving, and then I have to throw this away because obviously your diffusion parameters will not be correct if you're calculating the noise instead of the real change in signal. Okay. So now I'm going to touch just a little bit about beyond the diffusion tensor. So most people, when they think about diffusion, will think about tractography. And so what is tractography? Tractography is the use of the orientation information from the diffusion imaging to reconstruct estimates of white matter pathways in the brain. So here's an example of some very beautiful tractography from our DTI data. And this data, sometimes it can be analyzed with models other than diffusion, and I'll talk about that. And why would people do that? Well, there is a limitation to DTI that comes from effectively a partial volume effect. So here I have a cortical projection system of the left cerebral hemisphere, and I've put the typical voxel right here. And just with the naked eye, you can see that there's white matter tracks that are not in one consistent direction within that voxel. They're going in different directions. So if we have nicely aligned axons, then our water distribution will look something like this, and our ellipsoid fits that very well. But if we have axons, different tracks that cross, for example, then the distribution of the water would actually look something like this. But the ellipsoid we're going to calculate is going to be this kind of M&M shape. So one solution would be to increase the image resolution. If you can get low enough, then you can get a nicely sampled voxel with that, that's got less partial volume in it. This is an image from some of the work that we did a few years back where we did sub-millimeter DTI. We did not use single-shot EPI. We used a different acquisition method, fast-spin echo, radial fast-spin echo, to be able to acquire this. But you can see, if you're familiar with the optic system, so you got your optic nerves, and the two main optic nerves cross right here in the middle of the optic chiasm. And at this low resolution, we're actually able to resolve that crossing still using DTI. But typically what people will try to do is still use the single-shot EPI and go with a different type of model instead of the tensor to describe that distribution. So this is kind of a category of high angular resolution diffusion imaging or hardy imaging. You can go simply to multiple tensor models and model the data that way. Or you can go with non-parametric algorithms like MAP, which is mean apparent propagator, or diffusion spectrum imaging, or Q-ball, or spherical deconvolution. There's a number of them that are nice mathematical representations. So the goal of these is to directly reconstruct the fiber orientation distribution function, or FODF. So in that type of calculation, for a white matter that looks like this and has this type of distribution, you get this FODF. And for something that's like this, then you get these two, and the tractography, you'd come into this voxel and you'd go both ways and go from there. Yes, the angular dependence on diffusion. Yep, that's good. But there are other orientations besides crossing fibers that can be problematic for DTI. There's also fanning, so if you imagine axons come in and then spread out and go different directions, or kissing, so they come in and then go and touch and then go on. So besides these hardy type of models, there's also biophysical models like NODI, which is neurite orientation, distribution, and density imaging, or SANDI, which is soma and neurite density imaging. In the biophysical models, they break the tissue into different compartments and then try to give reasonable representations of those compartments, like sticks and the ball, and to say something about the axons and the density and the orientation of these different compartments. But if you want to extract more information, then you're going to need to acquire more data. Nothing is free, right? So some of them, you have b-values up to 2,500, 5,000 to be able to calculate those non-parametric models in Hardy. You need a lot more directions if you want to resolve multiple tensors or the shells of the Q space. So you need a lot more data, which takes a lot more time. I also wanted to throw in here at the end, mention that there are other ways to measure the diffusion of the water beyond that standard pulsed field gradient I showed you at the beginning, the two different pulses. For example, there's quadruple pulsed field gradients. So here's like the typical one that I showed at the beginning, the two gradients, 90, 180. And there's microscopic diffusion anisotropy, where they do fancy things, more complex things with the diffusion weighting. And that's such that they can pull out new information about the propagation of the water and then the tissue microstructure. There's also like oscillating gradient diffusion. So if you are one who enjoys theoretical development or mathematical modeling, diffusion imaging might be a field for you. And with that, it comes to the end. I want to thank Dr. Bandettini for inviting me to speak to you in the summer course, and then my collaborators and my colleagues who I've used some of their slides and content for my slides. And thank you for listening. So I don't know if there's any questions in. Yeah, sure, Pete.
It's nice to have a captive presenter to ask questions.
Yeah.
So you said that the minimum number of directions that you need is 6.
Yes.
And I've often heard the joke that if you want the best DTI data, it's like, how much time do you have? Like,
yes.
But given that today is 2024, on this particular day, is there a recommendation for like number of directions, number of shells, number of phasing codes?
Yeah, so as part of my job as staff scientist in the center, I often will consult for people when they want to come do a diffusion experiment. And we typically start with, what kind of question are you asking, right? So depending on what kind of question you're asking, then you might need a certain representation of your data. Then from that, how do we collect that data? How much do you need? If you want to just do DTI mathematically, you only need the minimum is 6. But there have been other papers that have been published that shows really to get a nice representation of the direction for brain tissue, that you need at least 30 directions. So, and because people move, like you saw there, we usually oversample because most likely you're going to have to throw some stuff away. So, we like to do maybe 60 directions, and sometimes more than one B value such that you can stabilize the fitting. But yeah, depending on the question you want to ask, which is why it's important to know what are you looking for. Because if you want to do some nice tractography through areas that are complex, well then we might need to collect more of a hardy type of data. Sure.
So, can you give an example of like what FA means in like the case of the cancer? What would that something like that mean in like a healthy volunteer? Like if I were to say stick me in the scanner and measure FA and try to relate it to some kind of cognitive behavior, like what does that mean?
Yeah, and I think that's part of when you read the literature is difficult because people like to take that anisotropy and say that it means all of your axons are intact, so your white matter has a high integrity. Or they like to do tractography and say, oh, now I've calculated a lot of, what do they even call it? Track number, I think, between these two areas, and so this must be a much stronger track. But it's hard to say something direct like that. We know from what a typical FA in certain areas of the brain should be, so you can say that kind of thing, and if it changes, that it's not normal. But what is it that changed? That's the harder part with diffusion, which I think is why there's so many different models that are trying to pull that out. And depending on the question for certain types of diseases, I think some of these models are definitely useful. Is it, are they truly measuring a change in neurite density? I don't know, but that parameter does correlate with this type of disease. So there's that. I think the harder part for diffusion imaging is that and I didn't even mention that so the SNR, right? So we've got bigger magnets, so we can have bigger SNR to start with, which is nice, even though we haven't done a ton of diffusion imaging on our 7Ts yet. People haven't wanted to, but I'm here if you want to try. And then the gradients that you're using, the stronger the gradients, the faster they can be, the better SNR we can get. And I think part of how the manufacturers calculate the diffusion, just very simple things about like how the images are reconstructed and whatnot. It's hard to compare across vendors. So, you can run a nice experiment on your scanner and tell what you expect that FA to be in your cohort, but to take that number and then go compare it to another location is difficult, which there are whole consortiums working on making that better, I think. Any other questions?
I'll take one more.
Okay, sure.
I've heard that there are disadvantages to doing diffusion at 17. Can you just, in like 5 sentences or less?
I think the disadvantages are more so just related to the EPI acquisition and the ghosting. So you saw the artifact from the FAT that I showed you, but regular EPI also has ghosting, the N/2 type of ghost, which maybe someone else had described. So that is stronger and harder to get past, I guess. So that can be difficult. Initially, people thought that the T2 would be faster at 7T, so that those echo times would it wouldn't be as much of an advantage. But when we first got a 7T, I did a comparative study, and it's better SNR. Maybe not as much better for fMRI, but it is better than at 3T, yeah. And if we get some fancy gradients on one of the 7Ts, then, yeah. Well, thank you very much for coming and listening today. No questions from the Zoom?
Nope.
Okay, all right. Bye.